Dear students, in the last class we have studied about the VSEPR theory, which gives the shapes of various molecules. When a molecule is having a shape, it is also associated with a bond length, bond angle, and also the bond energy or bond enthalpy. These are called bond parameters. In this class, let us study in detail about these bond length, bond angle, and bond energy. Coming to the first one, the bond length. Bond length is defined as the average distance between the centers of the nuclei of the two bonded atoms in a molecule. In an ionic compound, the bond length is equal to the sum of the radii of cation and anion. Example, in sodium chloride crystal, the bond length is equal to radius of sodium ion plus radius of chloride ion. In covalent molecules, the bond length is equal to sum of covalent radii of the bonded atoms. In hydrogen molecule, the bond length is equal to 2 into covalent radius of hydrogen atom. In HCl molecule, bond length of HCl is equal to covalent radius of hydrogen atom plus covalent radius of chlorine atom. Bond length is expressed either in angstrom or nanometers or picometers. Angstrom is 10 raised to minus 8 meter. Picometer is 10 raised to minus 12 meter. And nanometer is 10 raised to minus 9 meter. Bond length is also called bond distance or internuclear distance. In case of homonuclear diatomic molecules of A2 type, that is fluorine, chlorine, hydrogen, bromine, etc., bond length is given as DAA is equal to covalent radius of atom A plus covalent radius of atom A, where RA is the covalent radius of an atom A. Therefore, radius of an atom A is equal to the bond length between the two atoms A divided by 2. Therefore, the covalent radius is equal to of an atom is equal to half the bond length. Covalent radius of an atom A is half the internuclear distance. In another way, it can be given. In case of heteronuclear diatomic molecule of the type AB, bond length DAB is given by the bond length D between a molecule AB is equal to radius of an atom A plus radius of an atom B. Here bond length is equal to sum of the covalent radii of A and B atoms. Homodiatomic molecule with bond length. Let us take some examples. When I take the hydrogen molecule, the bond length of hydrogen molecule is 0.74 angstrom. Bond length of fluorine is 1.44 angstrom. Chlorine is 1.98 angstrom. Bromine is 2.28 angstrom. In ethane, between the two carbon atoms is 1.54 angstrom. in a nitrogen between the two nitrogen atoms is 1.50 angstrom. In hetero diatomic molecule with bond length, in case of HF, it is 1.09 angstrom. Experimental value is 0.92 angstrom. In case of HCl, calculated value is 1.36 angstrom and experimental value is 1.27 angstrom. In case of HBr, calculated value is 1.51 angstrom and experimental value is 1.41 angstrom. This shows that experimentally calculated bond lengths are smaller than the theoretically calculated values. This is due to the difference in electronegativities of atoms A and B, which is called ionic character in AB bond. Taking into the account the ionic character in AB bond, Shoemaker and Stevenson in 1941 gave the following empirical equation by which the bond distance DAB can be calculated. So according to them, the bond distance between A and B is given as radius of the atom A plus radius of the atom B minus 0.09 into electronegativity of an atom A minus electronegativity of an atom B. The validity of the above equation can be shown by calculating the NC distance in trimethyl nitrogen or ammonia. Trimethyl ammonia molecule is. Using the equation, the DNC is equal to the radius of nitrogen, that is 0.75, plus radius of carbon 0.77, that is equal to 1.52 angstrom. So using the Stevenson's equation, so 0.75 plus 0.77 minus 0.09 into electronegativity of nitrogen is 3, carbon is 2.5. So if you substitute these values, we get 1.475 angstrom. This value is in close agreement with the experimentally calculated DNC, that is 1.47 angstrom. Bond multiplicity or bond order is the sum of covalent bonds between the two bonded atoms. Many times we come across the word the bond order, which is nothing but the number of bonds between the two atoms. And we know maximum 3 covalent bonds are possible between the two atoms. Hence it is known as here the bond order becomes 3. If only one bond is present between the two atoms, bond order 1, 2 bonds are there, bond order 2, 3 bonds are there, bond order 3. The bond length between the two atoms decreases with increase of multiplicity of the bond. Example, the B single bond B bond length is 1.64 angstrom, whereas B double bond B bond length is 1.52 angstrom. Similarly, C single bond C bond length is 1.54 angstrom, C double bond C bond length is 1.34 angstrom, and C triple bond C bond length is 1.20 angstrom. So like this, the various bond lengths are given. This shows that bond length decreases with increase in the bond order. Sometimes bond order increases due to resonance and bond shortening is observed. Example, in benzene, bond distance between the two carbon atoms is 1.39 angstrom, which is intermediate between the C single bond C and C double bond C bond lengths. Here, this is due to the resonance structure of the benzene, which contains alternate single and double bonds. The bond length changes with the hybridization with the increase of the percentage of S character in hybrid orbital. The bond length decreases. Let us take the examples. If a molecule is having sp3 hybridization, which we learn in the later classes, meaning of the hybridizations. S character becomes 25%. So in the CH bond length, in this case is 1.093 angstrom. And the same CC bond length is 1.54 angstrom. If the molecule like ethene, where it is sp2 hybridized, where S character becomes 33.3%. Here the CH bond length is 1.087 angstrom and CC bond length is 1.34 angstrom. If I take ethyne, where the carbon atom is sp hybridized, where S character is 50%, the CH bond length is 1.057 angstrom and 1.20 for CC bond length. This shows that bond length decreases with the increase in S character. That means if the atom is sp3 hybridized, bond length is more. sp2 hybridized, bond length is less. sp hybridized, bond length is still less. Now coming to the another parameter, the bond angle. Bond angle is the angle between the orbitals containing bonding electron pairs around the central atom in a molecule. It is expressed in degrees. The bond angle helps in deciding the shape of a molecule. In carbon dioxide, the bond angle is 180 degree. Hence, it has a linear shape. In water, the bond angle is 104.5 degree. Hence, it has a bent shape. The bond angle depends upon the electronegativity of the covalent atom in a molecule. Increase in electronegativity increases the bond angle. Molecule, suppose if I take some of the examples. In case of ammonia, the nitrogen atom is the central atom whose electronegativity is 3. Therefore, the HAH, that is NH and H bond angle is 107.5 degree. The same molecule, that is PH3 phosphine, if I consider, where the nitrogen and phosphorus belongs to same group in the periodic table, but the electronegativity of phosphorus is less than ammonia, that is nitrogen. Because of the less electronegativity, the bond angle also reduces from 107.5 degree to 93.3 degree. In case of the arsenic hydride, so the electronegativity of arsenium is 2, the bond angle becomes 91.8 degree. In case of antimony hydride, the bond electronegativity becomes 1.9, bond angle becomes 91.3. Take another example, that is water molecule. In case of the water, oxygen is the central atom whose electronegativity is 3.5. hence the bond angle is 104.5 degree. The same H2S molecule, the sulfur is the central atom whose electronegativity is 2.5. Therefore, the bond angle becomes 92.3 degree. If central atom is less electronegative than the side atoms, increase in electronegativity decreases the bond angle. Yes, so this is another aspect where the central atom is less electronegative than the surrounding the atoms. Earlier case, the central atom is more electronegative than the surrounding atoms. Let us take an example, PCl3. So in case of PCl3, central atom is phosphorus, surrounding atoms are chlorine. The electronegativity of phosphorus is 3.0 and which is less than the electronegativity of the chlorine. Therefore, here the bond angle becomes 100 degree between ClP and Cl. When I take PBr3, so in case of the PBr3, the electronegativity of phosphorus is the same, that is a central atom, but the electronegativity of bromine is 2.8. The earlier electronegativity of chlorine is 3.0. So electronegativity of Br is less than the Cl and the central atom is having less electronegativity than the surrounding atoms. In such cases, the bond angle increases from 100 to 101.5 degree. In case of phosphorus triiodide, the electronegativity of the the iodine atom is 2.5 and the bond angle is 102 degree. If I take in a similar case the other example like arsenium chloride, arsenium bromide and arsenium iodide, so the bond angle increases from 98.4 degree to 100.5 degree and 101.5 degree. If I take nitrogen trifluoride, here the electronegativity of fluorine is 4.0 and in case of ammonia the hydrogen is 2.1. So because of this, the NF3 nitrogen trifluoride, the bond angle is 102 degree, whereas the bond angle in ammonia is 107 degree. Coming to the another bond parameter, that is bond energy or bond enthalpy or bond strength, all means the same. The amount of energy released when two neutral atoms A and B get bonded together to form AB molecule is called bond energy. Suppose if I take a neutral atom A which comes in contact with an atom B and results a covalent bond between the two, the energy is released. It means bond formation is energy releasing process because the molecule is more stable than the respective reactants. Since the energy is evolved during the reaction, it is written with negative sign. That what I said, bond formation is energy releasing process. Bond energy can also be defined as the energy required to break AB molecule into its neutral atoms A and B. The above equation can be given in a reverse way. If I take AB molecule and when I supply the energy, then these AB molecule splits into the A neutral atom and B neutral atom. In this case, the amount of energy that is absorbed to break the molecule, this is also called bond dissociation energy. It is written with positive sign. and it is also called here a bond is broken. So the bond breaking is energy demanding process. So in all these cases, this we call it as bond energy, which is expressed in terms of kilojoules per mole. If I take an example, Cc bond enthalpy is 3.48 kilojoules per mole. It means to break 1 mole of the C single bond C bonds, it gives the energy 348 kilojoules. So similarly, the OH bond enthalpy is 462.2 kilojoules per mole and NH bond enthalpy is 390.5 kilojoules per mole. More the bond dissociation enthalpy, higher the strength of the bond and higher the stability of the molecule. Bond enthalpy depends upon the size of atoms involved in bonding. When the size of the bonded atoms is less, more is the extent of overlapping of atomic orbitals during bond formation. This makes the bonds stronger, so bond enthalpy will be high. Let us take example hydrogen molecule. In case of the hydrogen molecule, the bond enthalpy is 435.8 kilojoules per mole. Whereas in case of the chlorine molecule, it is 237 kilojoules per mole. Bond enthalpy depends upon bond order. Higher the bond order, higher the bond enthalpy. That is, if I take C single bond C, bond enthalpy is 348 kilojoules per mole. If I take C double bond C, bond enthalpy is 619 kilojoules per mole. C triple bond C, bond enthalpy is 836 kilojoules per mole. This shows that increase in bond order increases the bond enthalpy. Bond enthalpy depends on the number of lone pairs on the bonded atoms. More the number of lone pairs of electrons on the bonded atoms, higher the repulsive interactions between them, which results less bond enthalpy. If I take a nitrogen attached to the other atoms where the 2 lone pairs of electrons are there, so in this case the bond enthalpy is 163 kilojoules per mole. And in case of the peroxides where the 2 oxygen atoms are there, each oxygen atom contains 2 lone pairs of electron. So in this case we have 4 lone pairs of electron. So as a result the bond enthalpy is less, that is it is 146 kilojoules per mole. That means increase in lone pairs of electrons in a molecule decreases the bond enthalpy. Breaking of similar bonds may need different energies due to the difference in chemical environment. Hence, in polyatomic molecules, the term average bond enthalpy is used. Example, in case of water molecule HOH, which is in gaseous state, so OH, it turns into the OH in gaseous state and H in gaseous state. In this case, the bond enthalpy is 502 kilojoules per mole. Now the same OH, further it turns into the O gas and H gas. Here the environment is different and bond enthalpy here it is 427 kilojoules per mole. Therefore, the average bond enthalpy in this case is 502 plus 427 divided by 2 gives 464.5 kilojoules per mole. This is a slide that shows the meaning of the bond length. It is the average distance between the 2 bonded atoms in a molecule. This shows the various bond length, bond strength correlation in hydrogen halides. It shows that the bond length increases with HF to HI and bond strength decreases from HF to HI. This is a slide that shows various the molecules which have the bond length and bond dissociation energies. This is also a table that shows the single bond, double bond and triple bond, their bond lengths. So it says the atom single bond between the two atoms has greater bond length, and double bond will be having shorter bond length, and triple bond is having still shorter bond length. And these are the various angles in the case of the molecules. So if a molecule is having a linear geometry, it is having 180 degree, triangular geometry 120 degree, tetrahedral geometry 109 degree, 28 minutes or 109.5 degree, square planar gives two bond angles 120 degree and 90 degree, octahedral gives 90 degree, and various examples in these cases. So this slide shows the shapes of various molecules and the geometries. This slide shows the examples: hybridization, lone pairs of electrons, regular geometry, and as well as the bond angles. The bond energies. This slide shows the average bond energies in various the bonded atoms. Students, goes through these things and try to learn about the various parameters, that is bond length, bond angle and bond energy. Thank you.